All right, so I'm delighted to introduce to you Jim Albert. So Jim is an emeritus professor. Oh, you don't want, oh boy, okay. We'll sign out of this one. So Jim is emeritus professor at Bowling Green State University. His current interests include Bayesian modeling and applications of statistical thinking in sports. He spends much of his retirement playing tennis. His best shot is his one-handed backhand slice. I understand he has a good net game too, so come on up. Thank you.
Okay, thank you. I had to mention tennis because Carl was a tennis player for many years, and so I think we had a lot of, that way we had something in common. Okay, so Carl, of course, if you know, he basically was well known for his work in exponential families, and I think he basically set the foundation for hierarchical Bayesian modeling, which is called parametric empirical Bayes. He was the chair of the Harvard Stat Department for a number of years, and he had a keen interest in applications in sports. So I'm going to focus on his interest in sports and his papers in sports. So I'll try to first give you some background about how I know Carl over the years. Carl grew up in San Diego, and he started becoming interested in sports in San Diego, so I'll talk about that. I'll try to give you an overview of Carl's best-known works in sports, and I want to focus a lot on his work with students through the Harvard Sports Analysts Collaborative. And anyway, I want to talk, and also he made a lot of interesting comments about the interplay between sports and statistics. I had the opportunity to interview him for a Chance article a number of years ago, so he talks about those interplay. Okay, so to get started, I was a relatively naive graduate student at Purdue, and my advisor was Jim Berger, and Jim Berger did a lot of work on Stein estimation, admissibility, and my task was to try to find like practical estimators for like Poisson means and that kind of thing. And Jim said, well, you got to read the articles by Efford and Morris because they were talking about practical estimation. So I started reading those papers real early in the 70s. So I knew about Carl's work pretty long time ago. And then I fortunately did graduate and got a job. And my first meeting, professional meeting, was in the University of Iowa. And I just happened to run into Carl there. And I remember I was just sort of surprised that he even wanted to talk to me because I was just a young professor and he was famous. And so but he was very friendly and outgoing and supportive. So I was pretty impressed a long time ago. And our research paths sort of, were in parallel fashion. I did a lot of work on hierarchical modeling for non-normal data. So did Carl. So we had similar interests. But Carl was always very active in sports issues. And so when the statistics of sports section started for ASA and we had our meetings, Carl was usually around. So he was always interested in that. And then I said in 2014, I interviewed him for a Chance article, and that's easy to find. If you just Google Jim Albert and Carl Morris, you should find that. Okay. Okay, so I got a picture of a all-star baseball spinner. So Carl and I both played this game growing up. This was one of the early board games, simulation board games, and every single hitter was represented by a spinner. And we didn't have the opportunity to use Ken Griffey's 1997 spinner, but we had people like Mickey Mantle, that kind of thing. And when you look at that spinner, the thing that always you look at is the size of the one thing, because that indicates a home run. So you like to have players that have relatively wide, one regions. Anyway, so Carl played softball and touch football's youth. He played tennis, and I think he played tennis for a number of years as an adult. So I'm very lucky to be I'm on the court almost all the time. So we're battling the pickleball players, but we but we still have his presence in tennis. Anyway, so Carl played simulation baseball like I did. His baseball team he went to was the San Diego Padres. Those days, it wasn't a Major League Baseball team yet; it was a minor league team, but it was a a minor league team for a major league team. So he got to see some of the great players like Larry Doby and Minnie Minoso came through San Diego. So he had some exposure to Major League Baseball there. Okay, now what's interesting is that that time the presence in baseball and statistics was Alan Roth. Branch Rickey hired him to be the statistician for the Brooklyn Dodgers. And so he was the first statistician to work full time. There was a big article in Life magazine about this. And so Carl thought this was statistics. Be a statistician meant you work for a baseball team. But then he realized that there was only one person doing that. So it was like wanting to be a movie star. I mean, there was really no opportunity to do that. So he didn't understand that statistics was a broader profession than just baseball. I can relate to that because when I was in college, I didn't really understand what statistics was all about either. So I was just a math person. So anyway, he discovered that there are other paths to statistics besides baseball, and then he went to Caltech and then eventually to Stanford for his PhD. And I think he met Brad Effer and him were classmates at Caltech, and eventually they interacted as graduate students at Stanford. Okay, one of his early papers was on tennis, which was very appropriate because he was a tennis player. And this was called The Most Important Point in Tennis. Now, for those of you who don't understand tennis, basically a match consists of a series of sets. Each set consists of some games. In every game, you have points. And for some odd reason, we call those points 0-0, 15 love, 15-15, 30, things like that. I mean, anyway, so basically you progress to that, and basically you have to win 4 points to win a game, and you have to win by 2. And so anyway, what Carl wanted to do was to identify the important points, okay, the points that really which mattered to winning a game. Now, intuitively, you might think, well, I want to win the first point, that's important, or maybe I want to win the final point, okay? And so if you talk to different people, they'll tell you that certain points are more or less important. Well, Carl wanted to do this more mathematically, more precise. And so what he did is he said, well, I'll define the importance of a point is what's the chance that you win the game given you won the point, and you subtract the chance you win the game if you lose the point. And you define that difference in probabilities as your definition of importance. And then what he did is he basically did a probability calculation where he assumed that the server's got an advantage. Let's assume that the probability of winning a point is 0.6, which is a reasonable assumption. And then basically he just did a probability calculation. And what he found out was the most important point in a game is basically 30-40, which is 1 point behind for the server. That'd be the same as being advantage out. Okay, that's the most important point, and the least important point is 40 love. Now, if you look at empirical data now, you don't need to do the probability calculation. You can actually verify that. That's also to basically confirm that finding. Well, that idea of importance of a point. Now we talk about high leverage situations. So now we talk about probability of winning a game or a match or something. And so all sports now talk about win probabilities, okay? And by using that, we can identify points of high leverage. So this is really an outgrowth of what Carl was doing in tennis. And so there's a nice review article by Ballmer, Matthews, and Nguyen, which talks about the use of win probabilities in different sports. So here's a picture from Baseball Reference. This is a game between the Orioles and the Angels, which displays the win probability for the home team as a function of the inning. And you see this is interesting is that the win probabilities don't change much during the first part of the game, but then they change dramatically toward the end. And notice that some areas are shaded pink. Those are points that correspond to high leverage. Those are particular plays that really had a big impact on the win probability. It could be a home run or an out with bases loaded, things like that. So, okay. Now, probably Carl's most famous sports application in the literature are the one about batting averages. And so basically, Carl and Brad Efron had these estimators which were good practical estimators of means, which basically are called shrinkage estimation. And they wanted to demonstrate that these things really work for real data. And they were trying to think of a nice example that people could relate to. And so they said, well, why don't we look at baseball? Because there's so much baseball data. Okay, actually the estimator they'll be doing is what was called the James Stein estimator. It was a collaboration between Charles Stein and a grad student, James. And that was one of the early closed form practical estimators of means. And if you looked at those days, this is before internet, in the 70s. So we had box scores that were published in the daily paper, but you didn't have everyone's hitting stats. You had to wait to Sunday. Sunday paper, usually in the back, there were these big tables of batting averages, including all the basic baseball stats. And so that was their source of data. And now here's the estimator. So the background is you want to estimate a collection of parameters, which we call theta 1 through theta k, and theta I. So basically, the naive estimator is just to use the sample means, which are the y bars, or yi, I guess. Yi would be the corresponding sample means. And so what you want to do is you want to get better estimators. You want to shrink them toward an average. And so that formula shows you that the estimator, the James Stein estimator, theta I hat, takes the overall mean, which would be y bar, and adjusts that toward the average. And the adjusting amount is this constant c, and it's a function of the number of parameters k. Sigma is the sampling standard deviation, and then you get the sum of squared deviations about the mean. Okay, so they wanted to demonstrate that estimator. Now, Roberto Clemente was the big star at the time. So they wanted to use Roberto Clemente. That day they looked at the paper, he had 18 hits for 45 bats. It's a 400 batting average. By the way, 400 batting average is sort of a magical number in baseball because nobody has really hit that for a long time. So anyway, they wanted to include Clemente, so they found all the other players that Sunday, which had exactly 45 at-bats. So it turns out they had 18 players who met that category, and they wanted to ensure the procedure they were using required equal standard deviations. So they wanted equal sample sizes. Okay, so here's a nice graph from their paper. And along the top, you see the observed batting averages. You see Roberto Clemente on the right. Max Alvis on the left. His batting average was 160, which was pretty bad. But of course, we know after 45 at-bats, you don't expect those, if you want to estimate their batting abilities, you want to adjust those toward the average. So here, you see you got relatively strong shrinkage toward the average. And so the estimates of the true averages are more like between 240 and 290. Okay. So again, and this particular paper really got a lot of attention, probably because it was relatively easy to understand. Even people that didn't understand baseball really appreciated this example. Okay, now nowadays, how would you fit this data? Well, we would call this a two-stage multi-level model. YI is the number of hits. You're going to assume that's binomial. And then you're going to let the logit of the probabilities be equal to mu, which is like an overall value plus a random effect, which we call gamma I. You put a distribution on the gamma I's. And then you put weakly informative priors on mu and tau. And he just used Markov chain Monte Carlo. Standard is a popular way of fitting it now. But essentially, you get the same results. And so the posterior mean of the PIs are similar to what you get through the James Stein estimator. Okay, now, probably Carl's best-known paper, or most highly cited paper, was the one on parametric empirical Bayes. And this is basically set the foundation for hierarchical Bayes and estimating the parameters by means of frequentist methods. And so he wanted to illustrate, these procedures that he was talking about in this paper. And so he talks about baseball again. Okay, now Ty Cobb was a famous hitter, and he's noted for being a 400 hitter. Now, he obviously was a 400 hitter because his batting average was over 400 for a few seasons. So obviously, if you ask that question, that's sort of silly because obviously he was a 400 hitter, but that's not the question. The question was his batting ability ever larger than 0.4? So we're not talking about his observed average, we're talking about his ability. Maybe Ty Cobb was lucky. Maybe he wasn't a 400 hitter, he just happened to have one good season. Okay, so that was really the question. And so he was trying to address this by means of a multi-level model. And okay, so here's how I would describe the model in modern form. There are different ways you can write this model, but I'll let the number of hits for a certain season be binomial. AB, sample size is number of bats. PJ is the probability. I'm going to model the hit probabilities by a beta function. Eta J is the mean, the prior mean of the PI, and the K is like a precision parameter. I'm going to let the prior means have a quadratic. Baseball averages over someone's career typically are quadratic in form. I'm going to assume a quadratic model. And I'm going to assign a weakly formative prior on the betas and on the precision parameter. And I'm interested in the posterior probability. What's the probability that the maximum probability is larger than 0.5? Okay, that's what. Now, he has a nice picture in his paper which illustrates these procedure estimates. And so I've done is I've redrawn this figure using R. And so the green dots represent the actual observed batting averages for Ty Cobb. The blue represents the quadratic fit. And again, this is like a shrinkage estimator. Because using a multi-level model, the posterior estimates shrink the observed averages toward the model estimates. So the red represents the shrinkage, okay? And if you look carefully, you notice that none of the posterior means actually are larger than 0.4. But the question is the maximum probability bigger than 0.4? Anyway, the conclusion is that he did an analysis, and yes, it's likely that his maximum probability was larger than 0.4. So the probability is like 75%. And I can replicate that conclusion through a more modern analysis. Okay, now, although we know Carl Musk for his baseball work and his tennis work, he really was working on a lot of different sports problems. He had a system for scoring tennis matches, and it was something you could use like a handheld procedure you could easily score. If you're interested in scoring tennis, by the way, Jeff Sackman is the guy to talk to because nowadays he has a whole database of tennis matches, and every single stroke is recorded of a tennis match. And about a year ago, I had COVID, so I spent a lot of time in my daughter's bedroom looking at a YouTube video and scoring a tennis match. So that was interesting. So some of my submissions are up there. He's got literally thousands of matches that are scored. He talked about NBA game, there are a lot of hills and valleys, momentum shifts, and he computed the probability of a comeback in a game. Carl had his own formula for how you evaluate a player in terms of runs per game. So you could basically, if you had 9 Roberto Clementis on your team, how many runs would you score? He's always enjoyed Bill James and used James results, and he used Pythagorean formula. Formula was for how you relate runs scored to wins and losses, and by using that, he tried to predict overtimes in different sports. And there's a paper where he talks about improving park factor estimates in Major League Baseball. So he worked on a variety of problems, and so you can find some of this work in different locations. Now, probably one of the most things that really impressed me about Carl was he really loved to work with students. And I think many years ago, Fred Mosteller was a Harvard statistician who liked to work in sports also, and also worked with students. And so following Mosteller's lead, Carl founded his undergraduate sports club in 2006. And it was just a place where they would meet regularly to talk over sports, issues. It was just a nice opportunity. And this organization is still very active today. They worked on all sorts of sports issues. I mentioned something here, team ranking, player evaluations, salary predictions, injuries, all sorts of things. And to show you they're still active today, here's their homepage. And they regularly post articles about different things in sports. A lot of people from this club are now working for sports teams. Is really where they got their start. It's really remarkable. And I think the best way of explaining how good our Carl was with students is to actually talk to the people who actually were part of the club. So here's some testimonies. Mike Daniel Adler is currently the assistant general manager for the Twins. And I'll just pull out a couple of things here. My life and career in life would not be the same without Carl Morris. He equipped me with knowledge to understand important statistical concepts and how they apply to sports. He was a true mentor and friend. And again, emphasizes that many people from this club went on to be to work for different teams. He spent countless hours in various common rooms and adding his informed perspective. Ben Blatt, Carl was patient and generous enough to lend his expertise to us, undergraduate students. And one thing that's interesting about this is that when Ben learned about Carl, he had practically no background in statistics. But that didn't matter. I mean, Carl was happy to work with them. And so really, they started learning statistics through sports problems. And I mentioned really Carl was sharp both in data and humor. Kevin Rader mentions that Carl took a band of students to see Moneyball. By the way, if you look at the book Moneyball, Carl is mentioned in the book Moneyball. So they saw a premature showing of Moneyball at Boston Common. So they were talking about had some conversation about parametric versus non-parametric fitting and survival analysis. And this particular student was struggling with the conversation, so Carl quickly shifted towards sports because, so he loved chatting sports analytics. So I think I was a professor at Bowling Green for many years, and we had some activity with students, but nothing like this. This is sort of a very special organization, and Carl was a really big part of that. Now, when I interviewed Carl Morris for that Chance article, we talked about the interplay between sports and statistics, and he made a lot of good comments about that. Whenever you teach statistics, you want to have good data sets, okay? And so sports data sets really are nice because people are familiar with the context and they understand the problems. And I think, so sports is really a very useful way of communicating statistics. If you use sports data, you actually can think about the application and the theory because you understand, how it's useful. So sometimes I'll do things in sports and I'll get answers in statistics that make no sense from a baseball perspective. And so it's important to think about not only the theory, but also the application. Clearly, you can't sports data is currently now big data. I mean, StatCast, for example, in baseball has got tons of information. And so there are challenges with working on that much data. And also you can't avoid some real issues, because these are real applications. And so you just can't make these simple assumptions and sweep under the rug. You have to really face those problems. Also, you learn about, by looking at sports problems, you learn about how people use statistics and probability. A lot of people are talking about drawing conclusions about, about sports. Right now, the big thing in baseball is all the injuries in pitching, and people think that it's related to the pitch clock. You hear a lot of discussions like that, and so you learn about how people talk about statistics, how they interpret statistics by reading all these analyses. And so these people who are talking about it, like people who publish in blogs, they may not be statistically trained, but they're very bright people who thought a lot about baseball. Bill James didn't have a real strong training in statistics, but he thought really hard about problems. And I think the fact his ability to pose really good questions made all the difference. So, but anyway, by looking at those analyses, that'll help you to motivate your own work. Okay, Andrew Gelman talked about had an article back in 2015 about Carl. He seemed ageless to us, both physically and his personal qualities. He wasn't young when he came to Harvard, but he had the enthusiasm of youth, and always was even-tempered. They were always very impressed with his maturity, and he always liked Carl's warmth, humor, and insights. So whenever I met Carl, saw Carl, he always had a smile on his face and was very easy to talk with. So I always admire his generous personality. I mean, he really genuinely wanted to work with people at all levels, and really helped in so much different collaboration, which makes all the difference in the world. Obviously, he was one of the first people to use sports data. I wasn't brave to do baseball papers until I was tenured, but now things have changed. Now we have journals that will publish these papers. He was very active in the ASA chapter. We had a statistics and sports section, which started in the 70s, and Carl was usually always there. And again, his work with undergraduates is remarkable. And I think you don't need to have a master's training in statistics. You always can talk about these sports problems and work on things. One of the stories that Carl told me is that he was really proud that he was one of the first readers of Bill James. And so Bill James, when he was starting, the way he got his abstract was he saw this little ad in the Sporting News, and this is the ad for this. I'm not sure this is exactly the one that he got, but this is a 77 baseball abstract, and included a table baseball game for $350. Okay, from Lawrence. He still lives in Lawrence, Kansas. And anyway, so Carl was excited about this and sent for it and got it. And Bill James sent a handwritten note to Carl, which said, "Dear Mr. Morris, I hope you enjoy the article, but if you don't, I'll gladly refund your $2. Well, not gladly, but I will refund it." So he was always, I wonder what happened to that handwritten note, but anyway. So here's some references. This is part of a paper that I'm probably submitting to JQAS, which talks about his contributions. I think you'll learn a lot through the interview. And there's that you can find in Chance, and again, it's easy to find online. So thanks.
So we have a minute or two if you have any questions or if anyone wants to mention any remembrances of Carl. If so, please raise your hand. Questions for Jim? Yes,
I just want to pick on Mark again. No. I did want to just tell a 1-minute story about Carl Morris. We were attending an ASA event at a friend's house not too far from Harvard Square, and it was the middle of winter, and we got hit with a blizzard. And the blizzard was so bad and came on so fast that essentially all of the public transportation stopped. And I had relied on public transportation to get home. And Carl was at this meeting, and despite the fact that it was so bad enough for public transportation to completely stop, it wasn't bad enough to halt Carl from giving me a ride home. And he really saved me from a wintry death that day. And I just thought I would share that story. Thank you.
All right, thanks, everyone. Let's give Jim one more.